That's funny, Jay. Is that a reaction to my meme of the day? And related to that, can you guys hear me okay on the voice chat? Anybody? Anybody? Yes, you can. Okay. Just checking my settings. We're good. We're good. We're good. And just quickly dropping the link into into the schedule, so it's there. That's the video link, of course. Okay, all right, that's updated. We're actually catching up, believe it or not. I mean, I know we're on von Neumann model, right? And that's going to get us into instructions. We are catching up. You can't hear us? Yeah. Am I not hearing you guys? Yeah, no, I can't. Let me, shoot. This happens every so often. I don't think I'm. No, that should be okay. Let me just try one other thing real quick. That's streaming. Okay, I'm going to kill Discord and relaunch. Okay, that usually fixes that problem. Hold tight. Okay, somebody want to just try to say something, see if I've got audio back from you guys?
Can you hear me?
Oh, yeah. Yep, I think we're good.
Can you hear us now?
Yeah. You hear me okay?
Sweet. Yep.
All right. Okay, let's do this. You know what's funny, by the way? It's October and getting to the end of October. Do you remember in August? And I think I asked you if I should let the beard go into full Santa mode. I don't know if you remember me asking you this question.
Oh yeah,
Yeah, I think you did.
I think I'm getting there. I think I'm seriously getting there.
I was all for it day one.
And I can certainly rock it. You know what I mean? I can absolutely rock the Santa mode. Just everyone's got their own natural assets, right? That they're bringing to bear.
True.
So
Got Colonel Sanders going on too.
Sanders, I got to trim my way. I got to trim my way to become the colonel.
Oh,
You know what I
later.
mean?
That's later though. Yeah, you got to do Santa first.
I got to do Santa first. Yeah.
Did you already go on set for The Chosen
So
yet?
no,
or-
I did that very first day, and then
Oh, yeah,
yesterday the schedules change, and it kind of canceled out.
of course.
They'll come back. I mean, it'll happen. It'll be at a different time probably, but
Okay.
yeah. So I was supposed to be there yesterday, and then I wasn't. So a little disappointed, but it'll come around again. Yeah, thanks for asking. It's been kind of a cool experience to just be part of that. It's just a different. I'm pulling up slides real quick. That's why I'm.
Has it been cool to be a hypocrite?
Yep, yep. I mean, I'm just playing myself, basically.
I would never think that you'd be a hypocrite, Dr. K, from what I've seen.
Well, thank you.
Yeah.
What's funny is, I did these short films for Vanderhall, and where are we at here? And I was talking to the director of those short films, and I was like, talk in the Vanderhall film. I'm this sort of older, kind of well-to-do father who drives a one of the Vanderhall cars, who's got this kid that wants to marry his daughter or whatever, and he's basically just a bit of a jerk to the guy. And anyway, I'm just like, when I was talking about the role of being a Pharisee, I'm just like, I kind of have to be, I'm older, I'm self-righteous, I'm maybe a little obnoxious, I'm probably wealthy, whatever. And I was like, basically, I'm just playing the same character I did in the Vanderhall films,
Oh my gosh.
just with the beard is all, and the and the prayer shawl and the rest of it. So anyway, okay, yeah. So it's cool. It's cool. It's something that I really enjoy doing. It's just kind of fun. Okay, we ready? We're ready to rock and roll.
Let's do this.
Let's do it. Okay, we are talking about machine code, machine instructions. Oh, right, Christmas Chronicles. Yeah, that's right. My grandkids already think I look like Kurt Russell in the Christmas Chronicles. I don't know. I should at some point, as we get closer, I'm going to bust out my Santa hat and my Santa glasses and see if it's not just rocking it all the way, because I think we're there. Okay, let's see. I think we got to that. We got to this right here. Isn't that right? That's right, man. Kurt Russell. By the way, I did a little bit of research because it was suddenly relevant. That's real beard, man. That's all Kurt Russell. That's not prosthetic beard.
That's crazy. He
Yeah.
did really good in with his beard in Tron. I really liked it. That.
Oh, I gotta go back.
He's-
Okay,
I'll,
I gotta go back.
I'll send a picture, but please
Yes,
continue.
drop the links, right? I did notice that as my beard's gotten longer, it's starting to get curly. It's like starting to get waves in it. So I'm just like, because of COVID, there's going to be no mall Santa business for me this year, So, never done the mall Santa. But anyway, okay. Let's see. We're talking about computer instructions, right? So this is the fundamental principle. Fundamental idea of all of this is, how we built, we got some, I think it's probably Isaac. I think we got some hot mic background interference going on. Just heads up on that.
Sorry about that.
No sweat. Yeah, so the idea, remember, we built all these circuits, right? We figured out how to do that stuff. And then we figured out how to do like control circuits. So you could have, stuff comes in and it moves around. It goes where we want it. Truth tables, so that with these conditions here, then these conditions are out the other side. When these wires are on and those are off, then on the other side of it, these wires turn on and these other wires turn off, right? That gets you decision logic, basically. And then we talked about how to make memories together, which we did. We made some memories. And when you have the ability to create this digital memory, we can put stuff in it, right? Remember with the RS latch and then the gated D latch, you could build this memory that could, as long as the power stays on, would just hold these values, right? And then that gives rise to this whole idea of random access memory. And again, we talked at the very beginning about these levels of abstraction and, peeling away the magic, right? Going all the way to the bottom and then working our way back up. You see how quickly you get all the way up to this part where we're now talking about computer instructions, okay? Once you have machine code or these machine instructions, now you have programming. All the rest of it is about the hardware, right? That's just the stuff it's burned into the system, right? That's on the semiconductor. That's on the CPU chip. That's just hardware. You take the chip, put it on the motherboard, and now you have this piece of equipment that you can plug in. But how do you program it? How do you make it bend to your will? And the answer is because in that same thing, as part of the control unit, is this logic that knows how to handle these machine instructions. And where do we put the machine instructions? Well, in memory, of course. And we just put them in memory. Take our program, write our program, put it in memory, and then just tell the control unit where to start. And what's it going to do? Fetch, decode, execute. That's the cycle. Fetch, decode, execute. Then what? Do it again. Increment the program counter, do it again. Now what? Increment the program counter, do it again. Now what? 1 billion times a second, just do that. And that's programs. That's how we do programs. But this is the most fundamental place where you can program the computer just by putting 16, in the case of the LC3, 16 bits, but it's deliberate. We decided what that was going to be, and we wrote that into memory. And we can then string those together and do all kinds of stuff and basically create the building blocks that you can use to do for loops and, while loops and all the math and all the stuff, okay? Which is kind of cool, right? As that kind of like all kind of comes together, it's a pretty, I hope that you're having that. It's a pretty cool revelation, I think, to kind of see what's going on there. But so in memory then are these instructions. In the LC3, the memory locations are 16 bits. We have 16-bit instructions. In other environments, you might have 32, 64, usually a power of 2, right? But still, it's an instruction is in a location in memory, okay? And what we're going to talk about from here, I just want you to kind of, just like understand that that we're going to talk about the LC3, which is just, it's this made up, very small, very stripped down, runs in an emulator. We're going to run this LC3 is going to be our computer. That makes it easier for us to teach it, to learn the basics, and not be bogged down. I think I showed you the other day, right? The ARM64 document, which was more than 1,000 pages. So, so just understand that what we're talking about now is a computer, but not like computers. You can't just say computers have 16-bit instructions. No, some do. Most don't. I don't even know. Some do. It might even be that most do. There's a lot of embedded chips. Chips that are not like in a phone or in a laptop. You know what I mean? There's way more tiny little chips in all kinds of stuff, like my cool little Bose speaker here, or my, you know what I mean? There's over and over and over again. Here's a Fender tuner, guitar tuner, right? Chip inside this guy, right? Every piece of electronics has processors running, doing all the math and everything else. You tear it apart, there's going to be a tiny little motherboard and a little chip on it. So there's probably, the reality is, it's possible that most processors in the world actually have 16-bit instructions. That's possible. I don't know for a fact, though. Could be 8. Could be 8. For really, old, I don't even know. But there's way, it's like the insect world. You know what I mean? There's way more insects than there are, mammals or whatever. It's kind of like that with embedded. I don't know if that's a good analogy or not, but okay. So in these instructions then that live in memory, we put them in memory, and then we just tell the computer where to start, and then it just goes fetch, decode, execute. In the LC3, these are 16 bits. The first 4 bits are what we call the opcode. And everything else, we call them the operand fields. And all that really means is it's like all the other stuff you want it to do. Like the opcode might say add. And when you add, you're going to typically, of all kinds of processors, this is typically true. but certainly of the LC3. I have to give it a couple of register numbers. Like you got 8 registers. So when I do an add, I need to be able to tell you, for example, like, well, I need you to add register 1, register 2, and put the results in register 0. So
Quick question.
yeah, Chris.
Is there like some sort of universal ratio between how much of an instruction is opcode and operand? Like, for example, we have 16 here, opcode is 4, but
Yeah.
not all computers use 16 bits.
Yeah, exactly. No, that's a great question. Really, really great question. I'm going to say that okay. No, it really is truly a great question. Here's the thing. Look at it this way. Typically, the size of a memory location is going to increase by powers of 2. So you've got 16-bit, then like 32, then 64. And I think that the bigger the word size, right? The greater the addressability, as we sometimes call it. But the larger the word size, the smaller the relative portion is that's dedicated to instructions. And what I mean by that is when I have 16 bits, there's 4. That's 25%, right? But if I have 32 bits, I just doubled it, but I probably don't have, I might, but I don't know that I have, 8 bits for the opcode. Because, right, with 4 bits, I've got 16 opcodes, right? Because 2 to the 4th is 16. With 8 bits, I've got 2 to the 8th, which is what, 256? That's a lot of opcodes. And then if I go to 64-bit instructions, 2 to the 16th, you know what I mean? Like thousands of instructions, very unlikely. So I think as the word size gets bigger, the instruction size usually also gets bigger, but not at the same pace.
Okay.
Yeah. But yeah, it's a great question. Also, let me just say that, and I hope you can see right there that with 4 bits for the opcode, I've got, in fact, I think we actually asked, right, how many opcodes are there? And the answer is 16 or fewer. Okay, it's not 17 because we've only got 4 bits to do these opcodes, right? But we've got a lot of variability, in the operand fields. Like, for example, again, I was talking about doing an add. If I do an add, I have to tell you where to get the first number, right? Where to get the second number, and I do that by telling you which register that's coming from. Which register is the second number coming from? And then where do you want me to put the result? Okay. So that's information, right? So it means that I can do, in the same 16 bits, I could do every possible combination of the 8 registers, right? Where a value comes from one of those 8 registers and is added to a value from any one of the 8 registers, and the result is put back into one of the 8 registers. Now, the total possible combinations of that is going to be 8 times 8 times 8, right? Which is 2 to the 3rd times 2 to the 3rd times 2 to the 3rd, which is 2 to the 9th, right? Which is going to be 512. So they're literally, by just right here within this same 16 bits, and burning 4 bits already just to say add, and using 12 with the remaining 12, I can identify 512 different kind of combinations of doing an add. See the power? It's kind of crazy. This is the power of the exponential representation. 2 to the 12 still, 12 bits still means that in the operands, I've got 2 to the 12th possibilities, which gets me to what? 4,096, So I can say add, and then I got 4,096 different messages I could encode into that to govern how I want to do that add. Crazy. Not a lot of space, tremendous representational power. But yeah, I've got 16 instructions. That's it. Think about programming languages, right? You've played around with Python or whatever, right? So think about how many built-in things you had to know, right, to do Python. Even just for loop, while loops, keywords like, for something in range, right? While loops and whatever, various instructions, etc. It's a lot. And now just kind of go, oh yeah, 16 assembly instructions. That's it. Tops out. And it turns out in the case of the LC3 that there's actually only 15. There's one they don't even use. So, right. Okay. We talked about add, okay? I'm going to break it down. As always, I'm going to kind of just go. You can double back, online, look at it again on YouTube. And definitely stop me if you have a question right now. The odds are somebody else watching later on YouTube, certain cross-section are going to have that same question. So here we go. Here's the add instruction. Opcode 0001. That's the opcode for an add. Okay. Why? Anybody want to venture a guess as to why that's the opcode?
Because add is the most common instruction you'll do?
No. I'll go no on that one. And you may be thinking too narrowly. Think it more broadly.
Is it just social contract?
Boom. Exactly. Yeah. Just social contract. We just said look, we need to have an add. I don't know. Give it a number. You know what I mean? You got 16 options. Hey, anybody, what do you want add to be? How about 0001? Right? Maybe because it's alphabetically first. I don't even know. Right? Why do that? Is there something in circuitry? I don't even know. But it's just, that's the convention. We just said that's what, remember I said before over and over again that, you're like, well, how does the computer know what these numbers mean? No, the computer doesn't know what the numbers mean. Okay? But if I take the program counter and I point it to this spot in memory, and in that spot in memory, the first 4 bits go 0001, then the control unit goes, add instruction. I got this. Let me take it from here. I know what to do now. Okay? Social contract. But that's because the program counter pointed to it, and then the CPU just goes, hey, program counter's job is to point to the next instruction. I fetch it, I decode it, and I execute it. Right? So it's just social contract. So when we have that 0001, we all agreed that was going to be an add. Now here's the other thing about this. If you check this out, there's this DR is a destination register in both locations, and then SR is a source register 1. Now, so all that means is this is the where the first number's coming from. Now remember, we talked about this. There are 8 registers in the LC3. That's a small number of registers. Okay, for like a real high-powered, that ARM64. I don't even remember how many registers it has. It's more than 8. It's probably more than 16, but so I've got to tell you where the first number's coming from, right? That's one of the things we know I have to say. And the other one is, where's the answer going to go? Where am I going to put it? But you're like, what is this over here? This is exactly the same in the red box, but what's going on over here on the right-hand side? Okay. And this is a way, again, remember we said we got like 500 different ways of dealing with these remaining 12, no, the 12 bits gives us about 4,000 possible ways, right, of encoding this remainder of everything. So what we do is we just the LC3, folks that designed that just said, well, let's always have these first 3 bits represent the destination register. Let's have the next 3 bits represent the source register, kind of no matter what. But there are some situations where I want my second operand, the first operand, right? When you do an add, there are 2 operands. I want the first operand to always be a register. But sometimes I would like the second operand to be just a hard-coded number. And other times I'd like it to be a register. So just chew on that for a second, right? Why would I want to, I mean, the notion that I'm going to take two numbers out of registers, add them together and put the answer back in a register, that seems pretty reasonable, right? That seems kind of straightforward. But why would I ever want to have, a hard-coded value, and we call that an immediate value, by the way. The IMM means, stands for immediate value. And that means I don't have to go look it up. I don't have to go to the registers to find it. It's right here. Whatever number is there, that's the value that I'm going to add into this thing. So why would I want to do that ever at this, in assembly language?
Is it faster that way?
Ooh, can be. Yeah, I mean, certainly, yeah. And let's go a little bit deeper, right? It's certainly faster than any other option. There's no question, right? As opposed to having that same value like in a register, right? Or out in memory or somewhere else, right? So yeah, definitely faster. And I mean, that really is the essence of it. But okay, so let me kind of build on that then and ask, what are situations that you can think of where I would want to just have this, a hard-coded value? What might be an example that you would already know from high-level programming like Python or C# or whatever you cut your teeth on? What do you think? I'm waiting. Yeah, man. So Jacob just said increment, right? Don't I often do this thing like kind of a for loop where I assign some variable like for I gets 0, right? And then I'm always incrementing that. I'm moving through. It's 0, and then the next loop it's 1, next loop it's 2, right? I'm indexing. I can also decrement because the number in here, by the way, this immediate 5, we haven't gotten there yet, but right there, that value in that immediate 5, that 5 bits of an immediate value, it's a 2's complement notation. That's a 2's complement number. Okay? 5-bit 2's complement number. So it could be negative, right? It could be a positive number, it could be a negative number. Could be -1 and I'm starting at the top and decrementing. You do that sometimes with for loops, right? You start at the top of where you're at. You like, hey, do this thing X number of times. Okay, give me X. All right, whatever X is, just start decrementing it until it gets to 0 or below, right? Give me your X. It's like 7. Okay, 7, 6, 5, 4, 3, 2, 1. When you get to 0, you're done. So sometimes you decrement to loop and sometimes you increment to loop. So, right, you could be moving by 2, by 3. You could be spitting out all the powers of 5. 5, 10, 15, 20, right? Just increment by 5. Do it again. You know what I mean? So anything where you know what that number kind of needs to be. And again, keep in mind, and this is what's so important. Remember we talked about sign extending? When you think about this, this is a 5-bit 2's complement number. If you want to think of that as 8 bits and it's 2's complement number, you just take whatever's in the sign bit and you extend it. You just add more of those to the left, right? Or in your case, is that the left for you? Yeah, I think it is. But anyway, that's the idea, right? But it's a 5-bit number. Okay. So what we do here is it's this bit 5, let's call it. This bit 5 is basically like a switch. It's a switch to the control unit. It tells the control unit, look, if you see a 0, then over here is the second operand register. Over here is the number that represents the second register for the source, right? But if it's a 1, then what's coming next is an immediate value. And that's just the control unit is the one that cares. So when the control unit's doing like the decode, right? I fetched it. Now I decode it. things like looking at bit 5 is an example of decoding, and figuring out what's the value I'm giving to the ALU to do this addition. Is it the value in register number whatever, or is it this immediate value, right? That's part of that decoding part, okay? And so, yeah, again, kind of here, when bit 5 is 0, then we deal with, we go grab this number that represents the register. This right here, see the zeros here on 3 and 4? That just means we don't care. I mean, it has to be zeros because of the way the circuitry is going to work, but they're just ignored. We don't deal with them. We don't care. Last question. Does it make sense to you that I've got 3 bits here? Literally, that's just going to be a number. Okay? The DR, SR1, SR2, it's just a 3-bit number. Okay, then that 3-bit number, what notation would you want to use? We already said that this immediate 5 is a 2's complement number, right? Because we want negative numbers. How about this register number? These 3 bits for the registers. What notation would you imagine that probably needs to use?
Wouldn't it be unsigned?
Yep. Yeah, exactly, right? I mean, there's no negative. What register were you going to use? -3. You know what I mean? It wouldn't make any sense. We're just like, look, there are 7 registers and they're numbered from 0 to 7, right? So you take this right here. So 0 to 7 identifies the register. That 111 as a 3-bit number, it's a 3-bit number, 3-bit unsigned number. If you said that was 2's complement, that number would be -1, right? Because in 2's complement notation, anytime you've got all the ones, that is always -1, right? No matter how many bits that is, right? Yeah, it's unsigned. It's just unsigned. So, and you remember when we talked about how big is a byte? And I was kind of saying, yeah, mostly when you say a byte, you mean 8 bits, but it's really good to just keep your brain a little more open to the idea that, bits don't just come in units of 8, where a byte has a value. In this case, I've got 2 bytes, which constitutes 16 bits. And then I've got a 4-bit number as an opcode, which you could view as an unsigned, or you could literally just view it as a bit pattern. You know what I mean? As a selection pattern and not even think of it as a number. That works. Then you've got 3-bit unsigned values here in the DR, SR1, and SR2 if you've got one. Bit 5 is a 1-bit value. And I don't even think of it as a number. I just think of it as like a Boolean. It's like on or off. Do I go left or do I go right? And if it's 0, I do that way. And if it's 1, I do that other way. You know what I mean? I view that more like a switch. And then I've got 3 and 4, which is a 2-bit. I don't give a flying rip. It's just 2 zeros. That's all, when bit 5 is 0, 3 and 4 are just zeros. And then this guy here is a 5-bit 2's complement number, right? So we've just done, when you look on the bottom, to me, there's 1, 2, 3, 4 different sort of social contracts at play. There's a bit pattern. There's an unsigned 4-bit bit pattern, 2 3-bit unsigned values, a Boolean switch, and a 5-bit 2's complement value. So if you've been locked into this, all values are 8 bits and they come in bytes, then this is just blowing your world apart, right? You've got to have the flexibility to be no, we can look at individual little chunks of this stuff, right? So anyway, and then once you sort of get past the shock of this new notation and everything, you can kind of start to see how this looks like programming, right? Because I get to write this instruction. And depending on what I say, the computer's going to do what I said, which is very, very cool. And I'm going to show you some examples of these live, and then you're going to write some programs literally as ones and zeros. Oh yeah. And
That seems so crazy to me.
right? Right? I mean, it really is. I mean, the earliest computers, the first personal computer was the Altair, which had a panel of switches. There were literally eight switches on the front panel that you would flip down for a 0, up for a 1. You'd write the thing in kind of like assembly language, encode that in machine language, put that into, ones and zeros, and then flip the switches up or down. And then there was this like thing you would push, and that would cause that value to go into memory. And then you could set the switches again and drop it in. And that's how you programmed the Altair originally. Straight up in binary. Now you're going to do it a little differently, and you're going to wind up probably with, hex values or whatever, but you're going to write some programs, tiny ones, little tiny programs, pain in the butt little programs that you're like, I could do this in 4 seconds in Python. Yep. But this will give you, but this is about understanding kind of what's going on. Now, it gives you that deeper conceptualization of what it means when we say programming. Because this is really what's going on down at the core. And you get to do it, which is cool and also tedious as hell. Get ready, because it is really, really tedious. But that's part. I want you to have a little of that tedium. You know what I mean? Just enough to kind of go, I know what that's like, and you then
Makes you more grateful for the higher levels of abstraction.
That's right. I'm trying to inspire gratitude in you. I would like you to appreciate languages like Python or whatever. Okay, let's do this one. What about this one? LDR. And by the way, typically with assembly language, machine language, assembly language, there is typically a 2 or 3 or 4, and most commonly 3, what we call a TLA, right? Which stands for 3-letter acronym. And then we have ETLAs. This is a joke. The ETLA stands for extended 3-letter acronym. This is what we use this to refer to 4-letter acronyms. They're ETLAs. But we do have this idea of these little acronyms, these little, mnemonic, LDR is load register. Add is add, ADD. There's AND, AND, and they're usually all caps. And this is just kind of the convention, right? Now, let me grab this real quick and throw it up there for you. This is in your book, and also there is a copy of this. Hang on, I'm just pulling up. Here we go. This is the cheat sheet. So this is like in the back cover, I think, of your book. I don't know what the resolution is like for you on this. Probably not fantastic, but so
Yeah, it's in the very back. Is when you just open it, it's there.
yeah, it's there if you have the book. And I also just put a copy of this just as a standalone PDF on Canvas. So if you don't have it, you can download that, right? But what you can see is essentially it's just a cheat sheet. There's add. What's the opcode? Right there. And we're doing LDR right now. It doesn't tell you anything else about it. It doesn't, you know what I mean? It doesn't, it's just a reminder. If you already know the rest of it, it's a reminder of what the format is. In the case of the add, right, we already talked about, it's got 2 entries because when bit 5 is 0 versus when bit 5 is 1, that changes. So there's two entries for add and 2 entries for and. By the way, notice that and add, all the formatting on the operands is exactly the same. The only difference is the opcode. Kind of cool, right? Because if you think about it, what are you doing with and? Give me a value, give me another value, I'm going to and them, and I'm going to have a result. It's the exact same. Operationally, it's the same. LDR over here for load register, that's its opcode, different. And it's got a destination register, and then a base register and an offset. That's the new thing. That's a new thing. But one of the other things, and you've got to get, when we start to get into programming and assembly, these are in that same, I have this appendix up there as well on Canvas. It's also in your book on page 526 of the second edition. It's going to show you how to write, what you should do when you're writing an assembly language. And then this will give you the format for the machine language. This will tell you the logic, right? If bit 5 is a 0, then, a certain thing. Otherwise, it's the other thing. And then there's this set CC, which is control codes, which we haven't gotten to. And then it gives you this nice detailed description. And then gives you, actual examples of sort of assembly language, okay? So all of these instructions, there aren't that many, all of them, there's LDR. All of those instructions are in the book, in that appendix, and that appendix is also on Canvas, okay? There's a section on Canvas with like files, resources, something like that. It's a finite search space. But again, how does LDR work, right? And it'll give you like a shorthand name, load base plus offset, which we'll kind of talk about. Okay? But this is your friend. This appendix is your friend. And I will never, by the way, when it's exam time, on the exams, this appendix, that whole appendix, page by page, is in, when you get to exam for module, whatever the modules are, I'm not expecting you, I think it would be absurd to expect you to memorize this bad boy right here. I think that would be really dumb to make you memorize that. It's pointless and you're not going to remember it. Stuff has a half-life of about 3 hours, So you walk out of your last final and by the weekend it's gone, permanently gone. That to me is a waste of effort. So this will always be open book in that respect, but this material is on the exam. Like you can go look it up. It's in like the questions at the bottom. Just have page after page after page. You can go look at it, double check it, you know what I mean, and then answer your question. Cool. Okay, let's go back here. The load register instruction. So there's the opcode, 0110. Now, here's the thing about loading the register. Load register, there are two different kinds of registers that operations that influence the registers. Let me put it that way, okay? There are load instructions, this LD, LDI, LDR, these are load instructions. And these ST, STI, STR, you notice they're kind of analogous, right? These are store instructions. So the easiest way to remember this is that it's all from the perspective of the register. So if I'm like load register, what does that sound like? Sounds like load truck. Okay, I've got this big ton of dirt, right? And the instruction is load truck. I'm probably going to put the dirt in the truck. That right? I mean, wouldn't that kind of make sense? And if I'm like store truck, I'm going to probably take the dirt out of the truck and put that stuff somewhere, right? If I say And that's kind of, I don't know if that even helps. But when I've got the load instructions, it's go out to memory and grab some stuff and bring it into the registers. That's how I get stuff into the registers. Okay? Store is how I take stuff that's in the registers and put it out into memory. Okay? So you remember when we were talking about how the relative memory speeds, like that, like the registers were like, in my pocket, right? That's the registers. They're just right here. I don't have to even move to just got to reach in my pocket, pull out whatever, that's the registers. But when I want to go out to memory, it's like I got to go down the hall to my office, right? If we're on campus, we're obviously not. But I would have to like go down the hall where it's slow. It's really, really slow to go out to memory, right? Even when it's on, the same chip, it's still way slower because of, and we'll talk more about this, but because of all the operations that have to happen, to get it out there, and then to go grab it and bring it on back. Whereas on the registers, it's all right there. It's like you go to the ALU, you there, go, and you're controlling it all right here. Okay, so what is entirely common, in the LC3 it's the only way to do it, but in other processors it's entirely common, is that math operations happen between values in the registers, the little scratch pads that are closer, right? The registers are close by. So I've got some math I got to do. I'm going to go out to memory and I'm going to grab that value, bring it in to the register. And now while I'm doing all my manipulation, I leave it in the register. So all the math stuff is happening really, really fast, right? I can't afford to do math by saying, okay, I want you to take something that's in my office and then something that's in, her office, and then add those together and put the result over in his office. That is just like, because I got to go all the way out there, grab it, bring it back, put it in the ALU. It's just too much back and forth. Whereas I bring things into the registers, and then I need to use it again. A lot of times there's a value and you reference it, repeatedly, and it's just there. I go get it once, I burn the cost, but now it's always close by. But most CPUs require most of the time that the math you do is inside the CPUs. Is in the registers. So loading a value into the register is a thing. And then to save that, store my value from my register out to memory is another thing. Okay? So when you look at, let me do this again. So when you look at this LD, LDI, and LDR, and actually LEA is also in that same category, what you're going to find is that these are just different ways of getting values into a register. Okay? And what that does is it introduces some different addressing schemes. And some of this is going to be, we'll kind of get to that, but it introduces different addressing schemes, right? Think of it this way. Remember the add instruction where we had, when bit 5 was 0, where did the second operand come from? A register. But when bit 5 was 1, where did the second operand come from? Right here, hard-coded. Those are two different ways of getting a value, right? One says, it's right here. It's hard-coded in my instruction. The other one says, I'm going to give you 3 bits. That's going to point you to the register where you can go get it. Those are two different addressing schemes, okay? Well, when we start having to go out to memory, there's other addressing schemes. I hope that makes sense. And that's what we're going to talk about with this PC offset 9 base register plus offset, and we'll get to all of these different load and store instructions, and you'll learn about these different addressing modes. Okay. That's just kind of a teaser, but I want you to, kind of understand where we're going with that. And then you find that there's a lot of power, especially when you've worked with languages like C++ or languages where you've got pointers and things, and you have to do pointer manipulation. Really, what they're doing is exposing addressing modes, in many respects. That really higher level languages like Python don't make, or Java even. Python's higher level than Java, but okay. So here's what do we do with load R. That's the opcode. This is 3 bits for the destination register, which means where's my pickup truck, right? What am I loading stuff into? That's the destination register. Then what I've got is a base register and an offset, okay? And we're going to go into more detail on this. I'm not going to even break it all the way down right now. Just want to introduce you to the idea that, the add instruction has one way of looking at it, this of the operands, and the load instructions start to play with other ways of looking at it. Now, the way this actually works, I'll give you a little teaser and we'll come back to it. But this base register, again, it's 3 bits right there that points you to one of the 8 registers. Now, in that register is the address in memory. So that register that we call the base register is literally just an address. Okay? And then there is an offset, which is a 6-bit value. It is a 2's complement number. And it basically says, go out to that spot in memory, and whatever that hard-coded value is, you're above that or below it by whatever that number is, right? You're just offset. So base register to get you to go anywhere in memory, and then the offset gives you some difference from that location identified in the base register, right? So that's another way of getting out into memory to get stuff. Very common for that offset to just be 0 because the base register points to the thing you actually care about. But there are situations where, many, where you want that offset to be something different, right? Like maybe the base register is the beginning of some data structure, and the thing you're looking for is always like, 11 bits into the data structure, and then your offset might be 11. So what I mean? The base register can now just deal with the structure, but the offset gets you into the structure at a certain spot. And then as long as you give it another address of a similar structure, your offset will stay the same. That's an example of why that offset can be hard-coded, but the base register, its contents can be changing. Okay? Okay. Now what I'm going to do is pause that discussion of the instructions to break down this fetch, decode, execute cycle a little bit more for you, okay? Everybody, you hanging? Are we hanging? We hanging with me? I hope so. And if not, double back. Go through the parts that you're not sure. Hit the TAs, hit me up, and we'll get to it. Okay, instruction cycle. Oops. I kept calling this a fetch, decode, execute cycle. That is the convention. That's what we normally call it. What this is just trying to show you is that there's a little more to it than that. And the reality is that not all of these happen with every instruction, which we'll get to. For example, not all instructions have to store a result, right? Not all instructions have to evaluate an address, or fetch the operands. But here's what's always going to happen. I always have to fetch the instruction out of memory. I always have to decode it to know what instruction it is and how we're going to deal with stuff. and I always have to execute it, which is where I actually run it. Every one of these takes one or more clock cycles. Remember back to whenever we were talking about where the clock circuit showed up, and that clock's going pulse, 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 like a billion times a second. And every time it goes pulse, it's like you turn the crank, and the whole machinery moves. You know, when we were doing the animations with the lines, right, that kind of a thing, where you're like a chunk, and then there's enough time for the electricity, the energy to propagate to the next state. Clock pulses, chunk, it does the next thing. So it takes time. Some instructions are very fast, other instructions are very slow. When in doubt, you favor, in assembly language programming and machine language programming, you favor the fast one over the slow one, okay? Even if it's a little less intuitive. Okay. So what I'm going to do is walk through each one of these, okay? And, you know, break them down in greater detail. And then we'll go back to some of the instructions. And in fact, I've kind of had this question in my mind. Yeah, we might. I think we will finish this lecture on Thursday. Today's Thursday. I think we will finish this. I think we will finish this lecture on Tuesday. That's what I said. Go back and look on YouTube. Yeah. Sorry.
can
Well,
check
it's
through.
only 2 right now. We've got till 2:15, don't we?
Yeah, it's not going to happen. We're gonna go over a little bit like we did last time, just to try to keep, you know, moving forward and catching up a little
Sure.
bit, so we don't run out of semester.
Are you saying we're stopping now, or
No, no. I'm saying that looking at the number of slides that remain, which is only like, it's only like 13 more that remain, and we'll finish those on Tuesday. We'll keep going right now till we're done. We won't finish, and on Tuesday we will. So what is this, module 5? Are we module 5? Yeah, this is module 5. So that's right. So module 5, the clock will start ticking on Tuesday. So the deadline is going to be a week. That's it. That's us right now, Jay. Thank you. A little gump for the soul. Okay. So what I'm going to do is talk about the fetch, decode, execute cycle in a little more detail. And I want to try to, hang on a second, I'm just looking ahead. Okay. All right. The fetch part of the fetch, decode, execute cycle is we get the next instruction from memory, and we put that into the instruction register. That's another register that's on the CPU. Okay. You can also think of it. I think of it sometimes as like, it's like there's this sushi table where you put the fish and you're like slice, slice, slice. You gotta bring it in from somewhere, set it down, and like process it. You know, figure out what to do with it. That's the dissection table maybe, or the, you know, it's your little workbench where you can put your stuff. Then. But here's how I do that. Here's how I do it. Remember this picture right here? Yeah, I know you have this memorized. But there's memory over here. There's that memory address register. There's the memory data register. Okay? And there's the instruction register right here. And there's the state machine that's running that whole thing. There's the program counter that holds the address of the next spot in memory where we're going to get our instruction from. There's the little incrementer, okay? And we'll break that down more. But so what do? We load the MAR with the contents of the PC. What that means is there's the MAR, that's the memory address register. That is the little register that holds the address in memory so that the memory can turn on that one word and turn all the others off. If you remember our little memory we built, there were these little lines, right? And it caused one to turn on and everybody else turned off. So that's what the MAR is. Now, what's the value we put in the MAR? It's the value in the program counter, which means we got to say the control unit has to go, okay, everybody, get off the bus, stop, don't look. Put the program counter on the bus. Now it's boom, it's everywhere on the bus. Now it tells everybody again, ignore that, nobody, don't mess it, don't write onto it, don't read from it, nothing happening here. Nothing to see here, folks, move along. But it does then tell that it tells the MAR to pull the value that's on the bus, right? And that's shown over here with load.mar. That's an instruction from the control unit that tells the MAR, go ahead and pull what's on the bus right now. That's for you. And it doesn't tell anyone else to pull it, so nobody else pulls it. Okay? It then increments the program counter. So now the value of the program counter, which was, where's the next instruction? We gave that to the MAR so that it can get that value out of the memory. And then the next thing we do is we increment the program counter. All right? So the incremented program counter is now sitting right here. This PC Mux, which is a multiplexer, it basically says, look, there's a number of different values that we might use to put into the program counter next time. Okay? One of those is the incremented program counter. That's why that's lined up here. Another one is some other value. And we'll kind of get to that. But, you know, why would you ever want to put a different value in the program counter other than the incremented program counter? Any quick guesses?
Maybe a jump instruction that would take you back to a different instruction?
Yeah, exactly. Jumping and branching. Because, right, all you do when you jump, you think of it a for loop, right, in Python. You know, you do your thing, you get to the bottom, right? It goes back to the top. And then it does some stuff, and it goes back to the top. And it just keeps, you know, for as many times as you loop, it has to change. If all you had was the incremented program counter, then all programs would look like this. Da-da, 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 done. You know? And if you wanted to do something 100 times, you'd have to code it 100 times, and you'd go start to finish. You know? There'd be no loops.
Question?
Yeah.
Are all programs going to be contiguous in memory, so it's just right up next to, like, every instruction is right after the other? Or?
No. Because I could do, think about it, right? I could go, you know, here comes my code, and I might have some data right here. Then before I get to the data, there's like this jump instruction that just like jumps me around the data and I can keep going. Or jumps me somewhere else. Or, you know what I mean? So it does not have to be together, but you do have to, you know, if you get to the part where you're done with that bit of contiguous code, you would have to jump to where you need to go next, you know. And anytime you do like function calls, right? Invoke a method, you know, call a method, call a function. Those are also just changing the program counter to go way the heck over wherever and then start running the code that's, you know, a method in some object or something, right? But all around that code is probably like the data for that object. You know what I mean? And then here comes another chunk of data and some other methods that aren't really it. And then when it's done, it returns control and goes back to where it came from. So it's kind of moving. It can potentially move all over the place, if that makes sense. Let's see. But sometimes, that's right. So we sometimes have to do branch or jump instructions. And so that means that if there's some other value coming from somewhere else, we might want to load that into the PC, you know? And again, the control unit and that finite state machine determines what is the new value that's going to go into the PC. let's see. Okay, all right, cool. So then the next thing that happens is that the word at the location pointed to by the MAR is moved into the MDR. What that means is we took the program counter, right? We put it on the bus, and then the MAR pulled it off the bus, and now that MAR selected that line in memory, and then the MDR has to grab that, pull that value out into this memory data register. Again, that dumb little 12-bit memory that we did is it. You just have to blow up the scale, but the concept's literally just that. Okay? Now that MDR has the value that needed to come. These are the same thing. I'm a doof. These 4 right here are the same 4 here. Yeah. Sorry, I'm confused. I'm confused because I made this slide. But I just realized. Okay, now the instruction register is loaded with the contents of the MDR. Because the MDR has the value that was in memory. What was in memory? An instruction. How do we know it was an instruction? Because the program counter was pointing at it. And whether it was intended to be an instruction or not, anything the program counter points at, we say, by golly, that's an instruction. And we go, we grab it, and we pull it out, we put it in the MDR. Then that MDR gets pushed onto the bus. That little gate basically says, it's the control unit has to give the MDR permission for that value to get onto the bus. Now that's on the bus, and then the control unit causes the instruction register to read what's on the bus. Boom. Now the instruction register has the instruction that was formerly in that memory location. That is just fetch. And you're like, fetch. Which is profanity for non-swearing folks. But I understand if you're feeling that way right now. Okay? So everybody with it, that is just the process by which an address in the PC causes an instruction from memory at that location to wind up in the instruction register. You see how there's a lot of steps, right? And why it's more expensive to have to go out to memory? You got to do all those, like, put it on the bus, tell this guy, everybody wait, tell this guy to grab it, right? Put it in the MAR, do the thing, grab the thing, MDR, back on the bus, right? That's a lot of steps. As opposed to, boom, you're just right there in the register. Yeah, go grab that one and that one. Boom, they just dump straight out. Okay, ready for the next part? Decode is the next part. Oh, I'm a little wrung out from fetch, right? Are you? Go back through it. Remember again, everything in 2810 is fluency. You're learning a language. You're learning a language of the computer. You're learning the language of the circuitry, of the hardware, of the architecture, of the instructions, right? Of the assembly language. It's like a compressed set of languages that you're trying to learn one after another. And the only way some of you speak at some reasonable level a language that you didn't grow up speaking, right? That you weren't born with, in terms of natural language, right? I do. The only way to do that is regular immersion. You can't cram and speak Portuguese in an hour or 10 or 100. You can't just say I'm going to spend 100 hours this week and I'm going to learn Portuguese. You'd be better off to spend an hour a week for 100 weeks learning Portuguese than to try to spend 100 hours in a week, even though it's the same amount of time. Way better off to spend, an hour a day for 100 days. You'd acquire some fluency if you did an hour a day for 100 days. 100 hours in 1 week, you won't. Because you got to have cook time. Your brain's got to have cook time for this to kind of settle in. Because the first time you see it, you're like, and then the second time it's like, oh, okay, maybe. Seventh time, you're like, okay, I think, yeah. 10th time, you're like, okay, ba-boom, 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 I got it. Okay? It's fluency that comes with exposure over time and consistency. So to do well in this class, again, mid-October, those that are hanging with are probably already doing okay. But the way you do well in this class is consistency on your own. Budget some time every day and hold that as an appointment that is like a due date. Make it a due date to yourself without having to be externally controlled by a deadline or an assignment or 5 points or something like that. Okay. All right. Decode. This is when we look at the instruction and we try to figure out what to do. And, remember we talked about decoders. That is literally what this is. Every one of those 16 possible opcodes has some input line that goes to, that is a decoder that activates a particular line. That then activates the line for the circuitry that controls that instruction. Okay? It's kind of like a big Rube Goldberg device, right? Remember these, it's like, remember Mousetrap? Remember the game Mousetrap, which was based on, what were called Rube Goldberg devices, named after Rube Goldberg, who was the guy who created these crazy elaborate, somebody should probably have a meme for this, but you know what I mean? Where you start by putting a little marble and it rolls, it flicks and stuff happens and, it goes on down, right? And in the game of Mousetrap, eventually it drops this little trap on the mouse, whatever, right? If somebody would like to drop, I'd invite somebody to drop something, picture, GIF, something of what it is I'm talking about. Really, that's what's going on here, right? The control unit grabs that opcode, uses that as a decoder to turn on the line that says, code for the add, go. Or circuitry for the and, go. Or circuitry for the LDR instruction, right? It just turns, and everybody else stays off, and it turns on. Yeah, that's a game of Mousetrap. Yeah, is that still a thing? Do you still have that in your generation? I had it as a kid. I mean, it goes back to like the 60s at least. I mean, that's when I played it. Yeah, there are more fancy ones.
Not really a thing nowadays.
Not
but
so much a thing. Well, not
No.
with not with like modern video games. It sort of pales, But
Yeah.
but there are
and
some.
Fortnite and all them, yeah.
Yeah, but there still are some pretty amazing, Rube Goldberg devices that you can find on on
Absolutely.
YouTube or whatever, right? But that's the idea anyway, because all this is really doing, again, the decoder is just like it's like you have 16. Picture that you have like 16 different, little little ramps, right? Little launch ramps, and one marble. And then this instruction, this opcode is like a little funnel that moves you to like, oh, it's an add. Then you dial it into this one and you drop the marble, and then it goes down the one that goes add. And everybody else is doing nothing, right? But it might be like an LDR, and you're like, okay, here the marble drops. There you go. And then the marble drops down, and the LDR does what it does. In fact, it'd be amazing. Good one, Morgan. Yeah, this is what I'm talking about. No, it'd be amazing. Sorry, I'm now watching the GIF that Morgan posted. No, it'd be amazing. Would be to build the circuitry, like build the circuitry out of marble drop, right? Can you remember all the animations when I'm trying to show you how circuits work? And I'm like, this line goes high, right? I bet it's been done. Has to have been done. Sorry, this just hit my head. Somebody has to have done that. But you get what I'm saying, right? So instead of that, it's like, okay, there's power coming here and here. So you drop the marbles, and that represents kind of electricity flowing. I don't know if it would work. I don't know if it would work. But it would be cool, though, right? As a teaching tool. I don't know. Okay. That's decode. Now, it turns out that you also have to, in some instructions, you have to do some address evaluation, okay? There are a lot of instructions that don't have any access to memory, in which case, you don't worry about that. But if the instruction does require, involve memory in some way, then you have to calculate the address. LDR was a good example, right? We mentioned the base plus an offset. We have to do an addition. You got to take the contents of the base register, take the offset, give it to the ALU, and add them together and like, okay, now that's the address location, right? Okay. And then, let me see. Yeah, this is the example right there. Right. I just went there, but there's the slide. And I don't think, I just wanted to show it as an example that the base plus the offset, you got to add them. That's all I was saying. Then I've got to fetch the operands, right? I've got the instruction. Fetching the operands, it depends on, what I have to do is dependent upon what the instruction is. So, for example, I got to do whatever I've got to do to get the operands. Where's my mouse? There we go. So, for example, when I do the LDR, right, where I'm loading register, I got to do a bunch of stuff that we kind of went through, right? Like, got to load the MAR, got to read the memory, put it in the MDR, move that to the destination register, right? Whereas an add, I just pull the source operands from the two registers. Like, it's 7, I go there. It's all right there on board. 4, right there. Give those to the ALU, do the math, put it back, and you're all right close by, okay? And I don't have to do all those other steps. But I do have to figure out how to do what I do. Hey, I'm going to do something I've never done